Okay, so today we will get a little bit deeper into colors, and the name of the lecture is color correction, but we will see a lot of colors here. So, well, you already know this concept that a color is a vector, and we can express it in the red, green, blue channels. That is simply a coordinate system, or we may have other coordinate systems that also serve to express our colors. So we will get today much deeper into this idea. So yeah, here you have this representation. So let's say that you have this color here that is in the RGB code. It is 184.95.12. So that means that if you think of it as a vector, so you have three coordinate axes. So you have the RGB coordinate axis, and then in that coordinate system, this color has these coordinates. And you can think of it as an algebraic coordinate system. So let me go a little bit slower in this idea. So let us make some drawing. Okay, so let's say that we have a coordinate system that we will call. I will do the analogy with the standard coordinate systems that you are used to in physics. So let me call x, and the bar is simply saying that it is a vector, and this would be y bar. This is z bar, and you know, in the x, y, z coordinate system, the coordinate of x is 1, 0, 0, the coordinate of y is 0, 1, 0, and the coordinate of z is 0, 0, 1. But these coordinates are in the x, y, z coordinate system. If I change my coordinate system, and now I have, for instance, let's say this other coordinate system, then the coordinates of the x, y, z vectors are different numbers. Okay, so it depends on your coordinate, on your basis for the vector space. So now let's say that. Okay, so let's remove this. So let's say that we have a vector that is our color vectors. Let me call it some letter V. So V, let's say that it is 3, 2, 1. So that means that it is 3 times x plus 2 times y plus 1 times z. And so we can have the same idea with colors. So with colors, we have similar representation, but now the axes are different. So now our axis will be R, G, and B, and they have the unit vectors. Those are the unit vectors in the RGB coordinate system. So this is 1, 0, 0, this is 0, 1, 0, and this is 0, 0, 1. And then if I have a color, that now I will call it C, then my color, that is R0, G0, B0, this is R0, R plus G0G plus B0B. Okay, so now R vector, G vector, and B vector are my bases in my coordinate system. Okay, so that is what we have in the slide. So this is exactly what we have here in this slide. Okay, so yeah, so there are some we can be more detailed about our vectors. So in general, we tend to think of this vector space as RQ. So we would say a color is something that, try to be good at the use of mathematics, okay? So you cannot say C is equal to RQ. So C belongs to RQ. Okay, so that would be an easy way to think of colors. So that means a color can take any possible value in the continuous range. But we can be more specific, for instance. So let's say, my colors can only take discrete values. So if you say that your colors are discrete values, then you have to restrict to set Q. So set is the set of integer numbers. Now let's say that my colors can only be represented with unsigned 8-bit numbers. So unsigned 8-bit integer numbers. So I would say, okay, it belongs to 0, 1 to 250, the Q. And there are a few things in this notation. So you use curly brackets to denote sets. And if you have to specify a set, and for instance, this one that has consecutive numbers, you have to specify the first two so that you learn what is the step, and then you have to say which is the last one. So you can put your colors in whatever space you like, but you have to be specific. Okay, so this is my color space. Okay, good. So so this is what we are saying here. So our RGB colors, they go from 0 to 255, and so we have 256 to the cube possible colors. That is 16 million colors. Actually, they could be arranged in this way. And actually, this 16 million colors, a person can see or can distinguish about 40 million colors, but not all of them at the same time. So you may remember yesterday that we were saying that our detector curve somehow shifts depending on what is the luminosity. So you can go up to distinguish up to 40 million colors, but not all at the same time because it saturates. Okay, so when you shift your curve, now you can see more colors. Okay, so what is so this RGB coordinate system is we are used to that, and here what we have are the three planes of so this would be the red-blue plane, this is the blue-green plane, and the green-red plane. And what we have is all the colors that are on those points. So for instance here, all the points in this plane. So let's go back to our drawing. So for instance, if I take any point in this plane here, any point there has the following structure. So it has R0, G0, and then 0. Okay, because it is on the plane, on the RG plane. And then if you play with R and G, then you have the colors that you have in the slide. Okay, so what about the CMY axis? So this is the cyan, magenta, yellow. So actually, that is a change of the coordinate basis. So now, instead of having the RGB coordinate axis, what we have is the cyan, magenta, and yellow coordinate axis. Okay, so we have the cyan, magenta, yellow coordinate axis. So that is only a change of the coordinate axis. And now, the same color has some coordinate in the RGB or a different coordinate in the CMY axis. So printing, so now we know that this is the coordinate axis that we use to display with light. This is the coordinate axis that we use to print on paper. So there is the same representation, so the same color in the RGB code has some coordinate, while the same point, so the point is the same, but now in the CMY coordinate system, it has different coordinates. Okay, good. Then, okay, so let's change an image with different in different ways. So the color of an image in different ways. Okay, so you may remember this color circle that we were discussing yesterday, and the ordering of the colors in the circle. You may remember that they are sorted according to our responses of our receptors. So let's say that we have that image, and this is the histogram of that image. The black one is the intensity one, or luminance, or whatever, however you want to complete that. And now, what we do is we shift just the red channel, we shift it, or we apply a gamma transformation with gamma equal 2. So with gamma equal 2, what it does is you are bending the identity transformation. So the gamma equal 2 is this one. So it is something like that. So this is the input color. This is input, this is output. And then you are shifting most of the colors up. So this would be identity. So if you enter with some red value, now red prime is larger than red. This is larger than the input. Okay, so now we should expect that the image is more reddish. That is what is happening. So now we understand these holes. These holes are created by regions in which the slope is larger than 1. These spikes where the slope is smaller than 1. And the rest of the histograms don't change because we have only applied this transformation to the gamma to the red channel, and in some way, we may think of this transformation as moving in this circle to the more red area. So we have somehow shifted all our colors to the more reddish region. And this is the original again, and now with gamma equals 0.5, so this is the opposite. So now, if we are decreasing the red, now what we are doing is moving in the opposite direction to red. So the moving to the opposite direction to red is moving into this cyan area. So that is why the image looks more like cyan. And we can apply this to the different channels. So the green, with gamma equal 2, with gamma equal 0.5, now we are moving more in the magenta area. Now more into the blue, more into the yellow. So Okay, so RGB and CMY are the only coordinate bases that we can have. And the answer is obviously no. So you can define any coordinate system that allows you to reach a point in that vector space. So RGB is one, but there are many others, and many of them, they follow this idea, separating one channel that accounts for the number of photons, and how to reach that channel. There are many different formulas. So you may use the value, you may use the luminance, you may use luminosity with a different formula or whatever. But one accounts for number of photons, the other one accounts for colors. So the other two accounts for colors, and you can put many different names. And in one of them is A star chroma, B star chroma. But in general, these are called the chrominance channels. So you should separate into luminance and chrominance. So luminance is number of photons, and chrominance is what is the wavelength of those photons. Okay, so we will see one, that is this luminance hue saturation. That it seems that it has some kind of physiological meaning. So it seems that the brain tends to see in this LHS system rather than the RGB. Okay, so actually it is funny because the first attempt to try to organize colors was done by Maxwell, the same one of Maxwell's equations. So he tried to organize in this way. And probably it is not the organization that we would choose today, but it was a very good attempt. So actually he already separated into red, green, blue channels, and that was mid-19th century. So he had a very good intuition of how things work. Okay, so now we will use this system, this luminance hue saturation. Okay, so in the luminance hue saturation, we will have some color space. That in this case it is a triangle, and we will see where this triangle is coming from. And then there is a point in that triangle that is gray, and it is always in the middle of the triangle. And then your color, we will define it as how far you are from the gray point, and we will call that the saturation. So the farther you are, the more saturated you are. And the other one is, what is the angle between there is a vector that goes from the gray point to the red, the more red point that you have in the triangle, and then what is the angle between this vector and this vector? And the angle has to be counterclockwise. Okay, and that angle we will call it the hue. Hue in Spanish is tono. ¿Cuál es el tono del color? ¿No? Okay, so let's see how to where this triangle is coming from and how to define all these things. And again, this is not the only representation. So there are many that make this the composition of luminance and then hue and saturation, or the one we will study is this one, HSP, that is hue, saturation, and value. So we will use the value instead of the luminance. But there are many. We will see one of them just to get an idea of how these things are constructed. Okay, so now let's go back to our color space. So we have here the red axis. You see that? So the origin is here. So this is the 0, 0 point, 0, 0, 0 point. And then we have the red axis, the green axis, and the blue axis. And then we may think, for instance, all the colors that fulfill this equation. R plus D plus B is equal to some C value. So you choose C, and then you look for which is the set of colors that fulfill this equation here. And that will be plane. So that is the equation of the plane. So which plane is that? It is in particular this one when C is equal to 255. Okay. So all those colors here in this plane are the ones that have the equation, that fulfill the equation R plus D plus B is equal to C. And yeah, you know how to compute the value. So the value is the average of the three channels. So it is the same as R plus D plus B divided by 3. So the value has to be C divided by 3. Okay. Okay, good. So that is the plane that I was showing before. So this plane here, or this triangle here, is the set of colors that fulfill R plus G plus B is equal to C. Okay, and I can look at the intersection of this plane with different entities in the vector space. So for instance, let's look at the RB plane. So the RB plane is this one. So it is defined by R and B. So what is the intersection of this plane with this? So the plane R plus G plus B equals C with the plane RB. What is the equation, by the way? What is the equation of R of the red-blue plane?
Green is 0.
Green is equal to 0. Yeah, that is the equation of that. Okay. Then, yeah, this is the equation there. Okay, so I have actually, let's go our whiteboard. So let's try and do it in the same way. So this was red, this was red vector, this is blue vector, this is green vector, and then this plane here. So this plane here is the plane G equals 0, and we had another plane that was the R plus G plus B equals C. So the intersection of two planes has to be a line. So now let's look for that line. Oh, that's great. Okay, so what is that line? So that line is this line here. And this line here fulfills for instance, we take the C equal to 255, we choose one C. And then, if we substitute G equals 0 into R plus B plus B equal 255, then what we get is R plus B is equal to 255. So this is this line here. And this line goes from completely red. So this point is the 255, 0, 0. And it goes all the way down to 0, 0, 255. What about if C is larger than 255? So if C is larger than 255, then the intersection of the R plus D plus B equals C plane with the color cube is no longer a triangle. It is an hexagon. So between 255 and 510, it is an hexagon. Beyond 510, it is a triangle again. We will see it in a moment. So here, just for the sake of example, I have he has taken this C equal 384. So for the particular value C equal 384, now we have this intersection that is an hexagon, and we have represented in the hexagon different colors that fulfill that equation. Okay, so then we can study what is the intersection between the hexagon and any one of the planes. So here we have taken again the red-blue plane that has the equation g equals 0. And for instance, this intersection is r plus b equals 383. Actually, I think there is a little mismatching. This is 384, but it doesn't matter. So it should be the same number as in both slides, but it doesn't matter. Okay, so yeah, what if we look at the intersection with some other plane? So for instance, the plane g equal 255. So now, instead of looking at this plane here, we are looking at this other plane. And the intersection is that line. So, and we can look at any other possible intersection. So we can see the intersection of this hexagon with respect to any plane of interest. Okay, so practices. So let me go to the document. Atrás. Bueno. ¿Qué ha pasado con el otro? No lo habré borrado ninguno, ¿no? Ah, no, que me he cambiado de asignatura. Me he cambiado de asignatura aquí. Ahí. Okay, so practices. So you can compute, for instance, these gamma transformations. Gamma transformation. Are they organized by lectures? Yeah. So this is lecture 5. Gamma transformations in the in one channel. And the other one is color cube and intersect.
Diferente en gamma transformations y individual de gamma.
Sorry, say it again.
¿Qué diferencia hay entre hacer una transformación gamma y incrementarla o bajarla?
La transformación gamma lo que hace es que te lo pone así o te lo pone así. Y incrementado o bajar el qué.
Gamma,
pues eso. Ah, sí, la verdad es que esta práctica es muy parecida. Había alguna por aquí arriba. Aquí, esta tuya. No hay diferencia, la verdad. María, te has quedado sin práctica. Es que es la misma que la de Gonzalo. Bueno, lo siento. Vale. Okay, so here what we have is the color cube. Now the origin is down there, and we have the intersection with some particular plane. And what we do now is to change C. So here you have the two different kind of intersections. So either it is an hexagon, or it is a triangle. Okay, so we go back to our color space. So let's say that we have a point P0, and this P0 has in the RGB coordinate system, it has R0, D0, B0, and if this P0 will belong for sure for one particular plane that is of this form, R plus G plus B is equal something. Actually, equal what? Equal R0 plus D0 plus B0. So the C is R0 plus D0 plus B0. Okay, so that is the plane, that is the one that is represented in black. And now, in that plane, there is a point that this line here is the 1, 1, 1 direction. So it is the diagonal of the cube. So this line here, the black one, is the diagonal, it is the 1, 1, 1. Where that line intersects the plane, that will be the center. That is the gray point that I was mentioning at the beginning. So here, there is a gray point. This is the point where the 1, 1, 1 direction intersects the R plus D plus B equals C plane. So now we have identified our center of rotation, and now we refer P0 to that center. And we measure what is the distance between P0 and the center, and what is the angle between this vector that goes from the gray point to the red point of the plane, to the more red point of the plane, and the most red point of the plane is the intersection of that plane with the r-axis. Okay, so here we have a point. This is a vector that joins the gray point with the red point, and now this vector makes an angle with this other vector. Okay, so let's try to formalize all that. Okay, so this point of intersection, the gray point, the gray color is a vector that we will call V0. So this V0, this is the vector V0, will have a module. So that module will be the V of the HSV color code. Then we have this other vector S0. The module of S0 will be the S of the HSV color code. And now we have to define the H. So the H is the angle between S0 and this vector. But who is that vector? Okay, so that vector is V0. Okay, so this is V0, the vector V0. And so it starts here and it finishes at the most red point of the plane. But that most red point of the plane has to be R0 plus D0 plus B0, and this is a scalar, and it lies in the red axis, so it has the vector R. Okay, is it clear? Okay.
Pero va a preguntar que si el R0, G0 y B0 es el punto P0. Entonces, del punto P0 tú haces, o sea, V0 de dónde es que eso es lo que no entiendo. O sea,
V0.
Sí.
V0 es este punto de aquí, y este punto de aquí, me lo he saltado. V0 es un tercio de R0 más G0 más B0, y luego, como está en la dirección 1, 1, 1, pues será R más E más B. Esa es la dirección 1, 1, 1.
Vale, entonces un tercio del punto P.
Sí.
Y luego...
Esto es C, esto de aquí lo habíamos llamado C.
Ah, bueno, vale.
Pues es C tercios, realmente es el valor.
Vale.
¿Vale?
Gracias.
Nada. Ok, let's see some examples. So yeah, let's say that we have this point in that triangle. Now the origin is here. No, the location of the origin and how to orient the object is arbitrary. So we orient it in the way that is more convenient for visualization. And then this is the color vector. So this is the P0. Then those are the coordinates in the RGB code. Then this is the line, the gray line that goes along the direction 1, 1, 1, and it goes from the 0, 0, 0 to the 255, 255, 255, and it is full of gray colors. So all the colors along that line are gray. Then we represent again the color we are interested in, and now we measure what is the distance, the vector that goes from the gray point of our plane to our color, and that will be the vector v. Then we join this vector v to the most red color in the plane that is the intersection of the red axis with the plane. So we join this point with this point, and we measure this angle, and that will be the hue. Okay, and now we have here the full representation. No, only with the red one. So that is a matter of definition. So the HSV color code, it measures with the red one. Okay, so yeah, so now let's look at some intersections, some more intersections. So let's say this is not an hexagon. This is just the 3 color planes. So this is the red blue plane, the green blue, and the green red. So those are the kind of the walls of the cube, the sides of the cube, and then we start increasing little by little the V. So for different V's, you see how it goes. At some point it is an hexagon, but this hexagon doesn't need to be symmetric somehow, so it has asymmetries. We're increasing V, then at some point it becomes a triangle again. Okay, good. So let's say that you have an RGB color code, and you want to convert it to an HSV color. Okay, so probably you already have an idea of how to do that, but let's formalize all that now with equations. So we define, so we have the point, the color code R0, G0, B0, and then we define C as the addition of the 3 numbers, and we define V0 as 1/3 of CCC, so that is a vector. And we define V0 as 1/3 of C, and you should note that this is not the module of the V0 vector. The module of the V0 vector is this thing, not that one. And so this will be the V. Then we define S0, that is our color minus the V0 vector, that one. Then we define S, the module of S, that is simply the module of this vector. We need now the angle. So we define the vector X and the vector x is C00, because it is in the red axis, minus V0, so this is what we have. And now we measure the angle between x and S0. And you know that the angle is the arc cosine of the dot product of the two vectors divided by the modulo of the two vectors. So, yeah, now you have some computational way of computing the HSV color code. So, given RGB, this would be V, this would be X, and this one, and this one here will be H. And now we have transformed the RGB into HSV. And which one is the one associated to the number of photons of the HSV? Which is the one associated with the number of photons? V, this V. Okay, so yeah. There is a note here that if C is larger than 85, then this intersection point is farther than the color Q, but it doesn't matter, it is well defined. Okay, so this is just a summary of all that. And it is difficult to normalize the saturation. So this saturation here, the saturation is the length of this vector. It is difficult to report not the length, but the normalized length. Right? It is again something of convention. So you can define what is the maximum length that I can have. So if you think of in all possible planes, what is the maximum length that you can have, you will realize that this is the maximum length. So this is the maximum distance that this vector can have. And the length of that saturation is 208. And then instead of reporting the saturation, you report the saturation divided by S max. So the saturation is a number between 0 and 1. And this normalization is fixed. So all colors are normalized in the same way. So it is a matter of how do you define your color code. And yeah, there are some small kind of small details of what happens if, for instance, x is 0, so this vector is 0, or s is 0. So then this is not well defined because you would have the arc cosine of a number that goes to infinity, or even it could be, so if one of the two is 0, you have 0 divided by 0, so that is an indetermination. Yeah, so there are small details in the encoding, but the general idea is clear, and we don't care about these small details. And the same happens with the arc cosine. So the arc cosine is a function that returns a number between minus pi and pi, and then you have to consider whether I am on the left side of this vector or the right side, and then take so once I compute the arc cosine with MATLAB or whatever computing system you have, how to make it that it goes from 0 to 2 pi rather than from minus pi to pi. But those are again small details that we don't care. Okay, any questions? No. Then we make a break. Now it is the opposite transformation. So from HSV to RGB. So let's say that we have an HSV color. So how to put it back into an RGB code? So we have to define, or we have to find some, what is the coordinate axis, or a suitable coordinate axis for an HSV color code. So one of those is this one. So that coordinate system, you see we have the v vector. So the v vector is the one going in the direction 1, 1, 1. Then we have the x vector. The x vector is the one that goes from the gray point to the most red point. And then we have y. And y, the definition of y is that it is perpendicular to the other two. So it is just the cross product between v and x. Okay, so in the coordinate system of x, y, v, the coordinate of x is 1, 0, 0. The coordinate of y is 0, 1, 0. Ora Marta, cuéntanos si te mata.
Venga, está diciendo uno. ¿Cuál es el café más peligroso del mundo? El espresso.
So in the coordinate system of x, y, v, the coordinate of y is 0, 1, 0, and the coordinate of v is 0, 0, 1. Then we have the HSV code. So we have H that goes from 0 to 5, S that goes from 0 to S max, and now we have a normalized saturation, and V goes from 0 to 255. And now, in that plane, so think of the X, Y, V coordinate system. In that coordinate system, the triangle is the floor. So the triangle lives in the XY plane. So this vector S in that coordinate system is simply S times cosine of H, S times sine of H, and 0. And this is in the XYV coordinate system. Would you agree with that? So if your coordinate system is the XYV, then this S vector is on the floor. So that is why it has 0 as the third component. So now, let's say that I want to put that S not in the coordinate system of the XYV, but in the coordinate system of RGB. So what I have to do is to the S in the X in the RGB. Let's do it on the Y. Okay, so let's see what we are doing. So we have a point, a vector S, but it is defined in the X, Y, V coordinate system. So this is a vector. And I want to put it in the RGB coordinate system. So let's say that this one has Sx, Sy, Sv. So those are the coordinates in the XY coordinate system. So in the RGB, and this is a general result of changes or of bases. So this would be S, X, that is this coordinate. Now times X, but now this X in the RGB coordinate system, plus Si, Sy, Y in the RGB coordinate system, plus Sp in the RGB coordinate system. Would you agree with that? So if I want to change the coordinate of a vector that is expressed in some coordinate system, what I have to do is to take those coordinates and multiply times the expression of the corresponding basis vectors in the new coordinate system. This is a generic algebraic result. Okay, so that is what we are doing. So I'm taking the coordinates of S and multiplying by the expression of X, Y, and V. But now these vectors have to be defined in the RGB coordinate system. Okay, so let's do that. Okay, so yeah, so this is the same. And now what I need is, yeah, this is nothing new. Okay. Yeah, this is only to say that the coordinates of x in the x, y, v, not z, x, y, v coordinate system is different from the coordinates of the same vector in the different coordinate systems. So that is nothing new. Okay, so I need to find these vectors, this expression of the vectors x, y, and v in the RGB coordinate system. Okay, good. So, yeah, and this is simply to say that I could also write this expression here. I can write it in a matrix form. So I can say S in the RGB is equal to some matrix times Sx, Sy, Sv. And who are the columns of this? So this column here is X in the RGB. The second column is Y in the RGB. And the third column is Z, not Z. V in the RGB. And this matrix in general is called the matrix of the coordinate system change. You may remember this result from algebra, right? Actually, now we are, so this is a vector, this is x, y, v. It is very complex. So you take your coordinate in the old system and you have to multiply by a matrix that is the basis vectors of the old system, but now expressed in the new system. So, yeah, this is this matrix A. Okay, good. So, what are the vectors that we are looking for? Okay, so V is the 1, 1, 1 direction, but actually we need the unit vector. So the unit vector is the 1, 1, 1 divided by the norm of that 1, 1, 1 vector. So the norm is 1 over the square root of 3, and 1 over the square root of 3 is the same as the square root of 3 divided by 3. Okay, so then x is perpendicular to v, and it has equal g and b components. Okay. So you can encode that. So I'm not going to solve that problem, but so we need an x. Let's use a encode, otherwise it gets too. So x is perpendicular. So the vector is. Let's say it has some colors Rx, Gx, Dx that we don't know yet. And what we know is that it has this same green and blue components. So actually, this is not like this. It is Rx, Gx, Dx. And we know that it is perpendicular to V. So V is perpendicular to x. How do I encode that? So what is the equation? If two vectors are perpendicular to each other,
And one is -1 divided by n2.
Equal to 0.
equal to 0 what?
Y escalar.
The,
Yes.
the inner product is 0. So this implies that V times X is 0. And this we have, well, we are looking for it. And V, we have it. It was square root of 3 over 3, 1, 1, 1. So this product must be 0. How many equations do we have? How many unknowns? We have only one equation, and we have two unknowns. Does it make sense? Yes, because we are looking for a vector. So let's say that this is V. We are looking for a vector X that is perpendicular to V and fulfills some particular pattern. But if this vector fulfills that pattern, this other vector also, and this other vector also. So probably not this one, because we would need different signs in it. But all these vectors, they fulfill the same equation. So we have to impose some other constraint on X. What is the constraint we need? The module has to be 1, so it has to be a unit vector. So X must be 1. So that means that Rx plus Gx plus Dx has to be 1. And now we have two equations and one now, and there is a unique solution. And this is the solution. So the solution is this one. Okay, so now we have X, we have V in the RGB coordinate system, and Y is simply the cross product between the two. So we now have Y2. So now we have the three vectors. This is the matrix, and now we simply have to multiply the coordinate system of S, so the coordinates of S in the XYV coordinate system, times this matrix, or this matrix times the coordinate, the X vector S, to get the S in the new coordinate system. Yeah, that's it. And what is the color? Because this is vector S, but we don't want S. We want the color of P0. So P0 is S plus V. You may remember S is here. So it is V plus S is P0. So now we have our color. Okay, so let's have some fun now with colors. So let's take a plane, a particular plane, R plus T plus B equal 384. So it is this hexagon, the intersection of that plane with the color cube. And now I can, yeah.
I don't get where the components of the matrix come from.
So it was here. Sorry. It is here. So the columns are the expression of X in the RGB coordinate system, the coordinates of Y in the RGB, and the coordinates of V in the RGB. And that is what we have been computing before.
But when they are multiplied by the coefficient of the other.
By these coefficients here.
No, for example, in the slide
86.
Yes.
Yeah.
You have 0, square root of 3, and minus square root of 2.
This one?
Yeah. Where does that come from?
Yeah, this is simply because they have different denominators, and so one is a square root of 3 divided by 3, the other one is square root of 6 divided by 6, the other one is square root of 2 divided by 2. So if you take out kind of common factor, the common factor is the square root of 6 divided by 6, and then you can re-express the other, whatever is inside. Okay, so let's take this image. Now let's decompose it into the 3 color bands. So we would have the red channel, the blue channel, and the green channel of this hexagon. And again, this is a practice, a nice practice to have. So if you can, any one of you wants to make this drawing. So this is a slice. Which one? 87. So hexagon. Okay, so, but we can also represent that instead of the color bands, we can see the hue, saturation, and value color bands. I don't know where I pressed. Press F. Okay. And HSV. Okay, so now let's try to understand. So this is a plane. What was the characteristic of that plane? That R plus C plus B was a constant. So that means that the value is a constant. And actually, for that plane, the value is a constant. So that is the amount of intensity that you are receiving from that plane. And then for any color within this hexagon, you know that the middle is a gray point. So how far you are from the middle is your saturation. So this is the saturation. So how far you are from the middle. And here it has been represented as 1 over 255. You know that the maximum is 208. And then the hue is an angle. So it is the angle of your color with respect to the most red point. So the most red point here is there. So what is the angle between your S vector and this vector? So for all these points, we have a very small angle, and the farther you go into that direction, you have a higher angle. And again, it has been represented, just to make it wide, it has been represented in steps of 128 or pi divided by 128 steps, and then it has been mapped between 0 to 55. So this is just a mapping of the angle into the 0 to 55 scale. Clear? Okay, good. Yeah, now we are representing the hue with some colors, some funny representation. Okay, so now I can play with my colors, but now in a different way. So this is the original image, the original histogram, but now I can increase the saturation. So now I can take any saturation value. So you can, for every color, you can compute the hue, saturation, and value, and you can do a point process, but now on the saturation. So you take the saturation value and you increase it by 50%. So you multiply that saturation by 1.5, and you get a different saturation. And maybe because of the saturation, the increase of saturation, you have to clip your values up to 55. We have to do that. But yeah, So this is actually what has happened. So all the colors now are more saturated. They are closer, so the saturation remains. It is how far you are from the gray, or seen in a different way, how close you are to the RGB pure colors. So the closer, if you look at this color cube, the farther you go from this vector, the closer you get to the limits of the cube. So when you saturate your colors, this is what happens. You saturate your colors. This is just the way to express it. So I don't find any other way. And you get closer to the R, G, and B. And then you can decrease the saturation, and now you get closer to gray. Then we can, for instance, play with the hue. So the hue is the angle. So now you take every color and you compute the hue. The hue is an angle, and you add 60 degrees to that angle. Okay, so let's look at the hexagon. So we have this hexagon here. So let's say I have a red color here. And if I add 60 degrees, I become yellow. And if I take the yellow and add 60 degrees, I become green, and so on. So that is what is said here. So this is the original, but now by adding 60 degrees, the red becomes yellow, the yellow becomes green, and so on. And then you transform back into an RGB just to display. And here we are shifting by 120 degrees. So now the red becomes green, and the yellow becomes cyan, the green becomes blue, and so on. 180 degrees. So this is just a color inversion. So this is the color that gives the opposite response of our cells. Then 240, 300, 360 degrees. And then this is a histogram of, so let's say this is a histogram, but now this histogram is represented in a different way. So this is angle, but instead of putting the angles, we have put labels on the angles. So this is 0 degrees, 60 degrees, 120 degrees, and so on. So now, if I shift by 60 degrees, my whole histogram shifts to the right, and then more and more and more and more. And it is cyclic. So whatever comes out from this side, it comes back from this one, because of the periodicity of the angles. So another practice to do. So one would be you gently. And the other one is hue, I meant saturation. Then we have hue change. You can also have histograms. So you can represent the histograms. Let's see here. So you can have histograms of hue, histograms of RGB, and also show here the same. Okay, so let us now make color corrections. Okay, so let's say that we have an input image and we want to apply transformation that transforms the colors in the input image into different set of colors. So this transformation will be called phi. And at every point, we will apply a different transformation. And that if the transformation, okay, so we could apply a different transformation to each one of the channels, or we could apply the same transformation to the RGB code of that. So the point is, the transformation can be the same or can be different for each one. Okay, so for instance, let's say that we have this original image and we want to make it more green, more yellow, more red, more magenta, whatever. Okay, so we could have linear and non-linear transformations. So for instance, an example of a linear transformation would be simply a matrix multiplication that is a linear operator. And an example of a non-linear transformation would be applying a gamma correction to each one of the channels, and we could have different gamma factors for each one of the bands, or you can imagine any other combination. For instance, you may say, this is not probably very useful, it depends on the context. So probably this is not something you would do normally, but you could intermix in the same, so let's say J, that is the red of the output. So you could say, for instance, I want to do, I don't know if this makes sense, Ri plus Gi plus Vi. So, and then whatever other functions you want there. So, to compute the red, you may mix the input channels, you may not mix them. So here in the example, for instance, this is not mixing channels. So the red of the output is computed only using the red of the input. But here we are mixing the channels, for instance. So to compute the red, we are mixing the red, green, and blue channels. But this is a linear mixture. This is a non-linear. In this case, we are not mixing, but it is a non-linear transformation. Okay. So, for instance, let's say that I use linear transformations and I use this matrix. So if I use that matrix, what I'm doing is just a scaling of the red color. So I'm not mixing the three colors, the three channels, and I'm taking just the R0 and multiplying by some scalar. So for instance, let's say that this scalar is larger than 1, then I will become more red. So the red channel will now have higher intensity. So what I'm doing is, if you have a point, where is the original point? The original point is here. So we are increasing just in this direction. So now we are going from this point to this other point. And we can do the same in the other channels. So now we are going from this point and making it bigger in the green direction. We're going from here to there. But the other two channels remain the same. Same for the blue. And we can combine all of them. And you can put a general matrix. So something particular to these matrices is that they are diagonal matrices. So if it is a diagonal matrix, then you are not mixing the channels. But if you use a general matrix, but in general you would mix the channels. Okay, so we take an input value, an input red, green, and blue value. You see here the Greek letters, rho, gamma, and beta. And we want to produce red, green, and blue outputs, and it will be just a multiplication of the two matrices. Okay, so what if I want to invert that transformation? So if the color transformation exists, if the inverse of the color transformation exists, then you can recover the original one. So let's say that this color transformation has been done by light, let's say, and you want to invert it. So you simply have to compute what is the inverse of that. So let me show you an example. Yeah. So let's say that this was the original image, but you don't have it. What you have is this one, that is an A photograph. So this, the paper here is much older, the colors have degraded, but you want to recover these ones. So the forward transformation has been applied by light, and you want to invert it. So let's see how to invert that. So, okay, so let's say that you have pairs of correspondences. So let me go again to the example. So you know pairs, that you know what are the correspondences. So you know that this color here should actually be this one. So 17, 122, 114 has to be 17, 121, 117. Well, what is the main change here? In which channel? The blue channel. So in the blue channel, we have to make it more blue. And you have more correspondences. So this one should be that one, but again, it is mostly in the blue channel. This one should be that one should be that one, and so on. So in general, you will have a number of correspondences. So you will have some colors in J that should be these other colors in I. And you know the parents. Okay. So what you have to look is for a matrix such that when you take the 8 colors, you multiply by the inverse of that matrix, and then you recover the original matrix, the original colors. Do you agree with that? So I would like to find the matrix A such that when I multiply the old colors by that matrix, I recover the new colors. That is what I want to find. But probably, if I have many pairings, these cannot be solved exactly. If I have just 3 pairings, how many unknowns? Okay, so let's go to the y. Okay, so let's think of a pairing. So instead of A inverse, I will use A. That is much more convenient, but it doesn't matter. Okay, so this is the old color. So this is RJ1. This is green, I think, 1, and this is blue, J1. And I have to find a matrix that is A11, A12, A13, A21, A21, A32, A33, such that when I multiply by the old color, and the old color is RI1, RI2, and RI2. J I1 and B I1. So when I do this multiplication, I recover this one. So I want to transform this color in I, this color in J. Okay, so how many, if I have a pairing, how many equations do I have? How many? 3. So let's make, so this multiplied by this has to be equal to this thing. So I have I have one equation, and then this one multiplied by this one has to be that one. So that is the second equation, and the third one, let's write this thing multiplied by this has to be this one. Okay, so I have 3 equations. Which are my unknowns? The matrix. So actually, this is a convenient way of writing, but I could reorganize this equation system such that my unknowns become on the right as the unknown vectors. Okay? Okay, and so I have 9 unknowns. I have 3 equations. So how many constraints, how many pairings I need to fully define my matrix A? 3. So if I have 3 pairings, that will give me 9 equations, and because I have 9 unknowns, that will uniquely determine my unknowns, my matrix. And actually, I can reorganize this. Let's say that I'm given a second pairing or a third pairing, or even more pairings. So let me shift this up. So now, let's say that I have k pairings. So I have RG1, P, we have a second one. Now I have my columns in the minimum. So okay, so let's look at the sizes. So this is, let's put the sizes in order. So this is a 3 times k matrix. This is a 3 times k matrix. And this is a 3 times k matrix. And I can, in general, call this, or rewrite this equation system as matrix J is equal to A I. Okay? Okay, good. So how can I solve for A? So if I have 3 pairings, A is uniquely defined. So I can find the A that exactly brings these colors into these colors. But if I give you more constraints, you cannot find it. So when you take an eye color, so I have a, sorry. So you have an eye color, this is a vector, you multiply by A, this is not exactly Rj. There is a difference between the two. There is a difference. And you want these differences to be as small as possible. So for every one of the pairings, I want this difference to be as small as possible. So as small as possible, I can encode as, okay, so you take the norm of that vector, sum over all the pairings, and you want to minimize that. And you have to find what is the A that minimizes that sum. So this sum here is called least squares. This sum here is called maybe different one. This sum here is called least squares. And the name squares comes from there. And least comes from here. So squares come from there, and least comes from the minimization. So, what is there an easy way of solving that problem? This is an algebraic problem. There are many ways of reaching that solution. I will not show that this is the minimum. It is the minimum, but I will not show that it is. But you will understand pretty easily how it is constructed. Okay, so we have this equation system. So we have J is equal to K by, let's put the sizes. So this is 3 times K, this is 3 times 3, this is 3 times K. So in principle, I would like to multiply on the right by the inverse of I, and that would be it. Can I do that? Can I multiply on the right by the inverse of the matrix I? So can I write, for instance, okay, so all I have to do is J y minus 1. Can I write that?
No,
Why not?
porque J por I a la menos 1 no se va a poder hacer.
¿Por qué no?
Porque tú tienes K, multiplicas así, y aquí tienes 3, aquí tienes K, entonces sí puedes.
Hay una razón más fundamental que eso.
Ya no lo quiero, no quites.
Que y menos 1 no existe. Because the inverse is only defined for square matrices. And this is not a square matrix in general. So for an arbitrary K, this is not a square. So I have to play some trick. And the trick is the following. So let's multiply by I transpose. So I do J, I transpose, and then I transpose. And let's look at the sizes now. So this is 3 times K, this is K times 3, this is 3 times 3, this is 3 times 3 times K, K times 3. So now this is 3 times 3, this is 3 times 3, and this is 3 times 3. So now I can multiply on the right by the inverse of this thing. So I transpose and then I transpose inverse. That is equal. Now you have solved for the equation system. So now I have found the A that minimizes that sum there. I'm not showing that this is the minimizer, but you can believe it. Okay, so this thing here is called the pseudo-inverse of I. Actually, if you compare this one to this one, it looks has kind of the same flavor. But this one cannot be done because I is not invertible because it's not a square. But this one, I transpose, and unless it has a zero determinant, this is square. It can be inverted. If you want to put the full name is thanks to the people who discovered it, Moore Penrose. Pseudo-inverse. I think, but I'm not sure. I think this Penrose is the same Penrose that received this year the Nobel Prize in Physics. But I'm not sure if it is the same. Okay, so this is what we want to minimize. Yeah, for 3 pairings we can invert it, but if not, we need this kind of tricks. Okay, so let's see how it works. It is 90, so a little bit of that. So you find the pairings, you make the multiplication, and this is what you get. So this is the original, this is the correct. With 4 pairings. So now we have 4 colors. This one has to be transformed into this one into this one. And the slides you have before is instead of 4 pairings with just 3 pairings. And you see that it is not really the best. This is with 3. So with 3 you get something, but it is not really the best. So it is much better with 4. So the more constraints you give, the better your correction will be. So that's it.